Okay, welcome to Math341. This is lecture 16. So we have a lot to cover today. What I want to do is I want to talk about ways to view the material and problems a lot more than doing integration. For two reasons. One, you should be able to do the integration and can just do it at home. Or two, this is the 21st century. You're not going to do the integration at home. You'll just put into some symbolic package and it will do the integration for you. So I want to talk more about how do you come up with the calculations that should be done and try to give a high level view of what do we expect various techniques and methods to give us. Oops. So I will be talking about the Pythagorean theorem. So this is not going to be a continuation of the baseball lecture we had last time. This will actually be a mathematical result and talk about why it's worth spending some time thinking about that. We'll then talk about the gamma function, which we saw briefly when we did the Pythagorean formula for sports analytics. This is a generalization of the gamma function. One of the most important functions in mathematics. It's a function that's initially defined for integers, but it can be extended to be defined not just for real numbers, but for complex numbers. It turns out that there is a generalization, so you can talk about -1/2 factorial. That is not the number of ways to arrange -1/2 of a person when order matters. Okay, that only combinatorial meaning only makes sense when you have a non-negative integer. But the function makes sense for other values. And what's great about this is now that I have a function of a real or even a complex variable, the advantage of that is we can now use tools from real analysis or complex analysis to understand this function and then specialize to integer values. So this allows us to get great estimates on growth rates, for example. We will then talk about some of the most important inequalities in mathematics and probability, Markov's inequality and Chebyshev's inequality. These are ways to estimate the probability or to bound the probability that something happens. And whenever you want to talk about something, you need to figure out what is the correct scale to study things. If I told you you have a 93 average, okay, this is Williams. If I told you you have a 98 average, 99 average, are you happy? What information might be useful? What's the standard deviation? So for instance, is 100 the maximum that you can get? So average out of what? But even if the average is out of 100, what if I now tell you there's some uncertainty in my claim that you have a 99 or 98? What if my uncertainty is 103 and 100 is the maximum? Well, if my uncertainty is 103, 100 is the maximum and you have a 99, I've given you no information. If I tell you that I believe you have a 99 plus minus 1/10 of a point, now all of a sudden you're very happy. So when you're trying to get estimates, you need to know what's the mean, and if possible, what's the standard deviation? The standard deviation gives you the natural scale to look at things about the mean. And so Markov's inequality is a situation where we only know the mean, and that's when we have a non-negative random variable. Chebyshev is a bit more general, and we assume that we have not just the mean, but we have some knowledge of the standard deviation. It shouldn't be surprising that the more inputs we have, the better we can do. And so if there's time at the end, I want to talk about two algorithms which you might have seen in computer science or some other math classes, divide and conquer and Newton's method, which give a great example of how the more you bring to bear on a problem, frequently the better you can do. There is a cost. Otherwise, we'd always want to bring more to bear. You don't always have those additional things to bear. You may not have a distribution that has a finite standard deviation. You might have something like the Cauchy distribution, so that Chebyshev's inequality is not available. And so because of that, we have to be careful in terms of which results we can use. So the reason I want to start off with the Pythagorean theorem is to talk a little bit about dimensional analysis. So if you haven't seen this before, it's an absolutely wonderful topic, which gives you a sense of how to attack a variety of problems. Hopefully everybody has seen the Pythagorean theorem. The only real freedom you have is how do you want to draw the triangle? Where do you want to draw the vertical side going up? So a squared plus b squared equals c squared. How many of you could prove it right now if you had to? Okay. So this is the standard proof going all the way back to Euclid, over 2,000 years old. Copyright has absolutely expired on this. Like all geometry proofs that are good, there are auxiliary lines. And you have to figure out which lines to draw and why. Some are solid, some are dotted. Here's basically the same picture, but now they've used color. Color really helps. Okay, I may not know why they've drawn those lines, but I'm pretty sure that I should show that the two orange things are equal and the two non-orange things are equal. If you really like a geometric challenge, figure out how the hell they chose to divide things this way. It's pretty clear, I think, which things you're supposed to show are equal to each other. But again, when you're doing a lot of these geometric proofs, it's not always clear how do you proceed. In the era of AI, this is not as big of a drawback because AI can just try billions and trillions of possibilities. But when we're trying to use insight, how do you come up with these ideas of what to look at? This is probably my favorite proof. I saw this when I was a freshman in a physics class. So consider a square of side length a plus b. And we're going to assume that we know that the area of a rectangle is length times width. With a little bit of algebra, you can show that not only, whoops, I have not changed the size, that not only are these right angles over here, but with a little bit of algebra, you can show that these are right angles here and that you have a square inside. And so the area of the big square is equal to 4 times the area of a triangle plus the area of a smaller square. And so when you go through the algebra, you get a plus b squared is, each triangle is going to have area of 1/2 ab, so it's going to be 2ab plus c squared. And so when the dust settles, you get a squared plus b squared equals c squared. Can anybody name the most famous, in terms of politics, graduate of Williams College? Who's had the most political success? Yes. It was Garfield, right? What is he famous for? No, well, I mean, yeah, but so this is another geometric proof. I'm not going to go through that. He is credited with a proof of the Pythagorean formula using trapezoids. There may be a reason why I'm not going through some other proofs with his trapezoid proof. Okay, so this is a very similar proof to what we saw just a moment ago, but he is credited with a proof of the Pythagorean formula. There's lots of ways of proving this result. A lot of good math results, different proofs highlight different aspects of the problem. So we saw some, geometric constructions. We saw some, breaking it up into lots of different regions. How do you figure out how to break it up into these regions? At the end of the day, are you just doing a brute force calculation, or do you have a sense of why something is true? For a lot of times in probability, you could just go through and you can crank through these calculations, but you have a feeling for, is this answer reasonable? One of my students was working in an investment house years ago, and the answer just didn't look right. And it was good that he had such an intuition. There was a minus sign error in one of the calculations and things were way off. But you want to have that feel because it's so easy to have some bad input. So here, let me see if I can make this perfect. 5 possible formulas for the Pythagorean theorem. We know, of course, all of these are wrong. Can anybody give me a reason why some of them might be wrong? Yeah.
So right off the bat, the a squared minus b squared is certainly wrong because it implies that c gets smaller as b gets larger.
Good. So that one seems quite absurd. In fact, c could even be negative or even imaginary. So good. So 3 is right out. What else? Yes.
C squared equals a squared plus ab squared.
Okay, why is this one wrong?
Because that c squared equals a plus b all squared, and that implies c equals a plus b. And
wait, which one? This one?
Yeah.
But it's not 2ab, it's ab. If it was 2ab, I would agree with you. So in fact, you could use that to eliminate this, because then the right-hand side is quantity a plus b squared plus 108 ab. So if you look at that, your argument works to eliminate 5. What about the first one? What units should you think of for A, B, and C? They should be in distance. And what unit do you want to use for distance? Yeah, we really should say meters, right? We'll be with the rest of the world. So the left-hand side is of units meters squared. The right-hand side is of units meters cubed. That seems suspicious. What about the next one, a squared plus 2b squared? Yeah, we should be able to swap a and b. I would expect something to be symmetric. So just by looking at all of these, I would be skeptical of everything but the fourth. And as long as this number here is less than 2 in absolute value, I think it's reasonable. So here is a dimensional analysis proof of the Pythagorean formula. And this is a great way to attack a bunch of problems. So when you are given something, take a step back and ask, what do I know about it? What can I say about the functional form? What can I say about the relationships? Most of what I teach you, you're never going to use. I don't feel too bad because I can say that about what you're going to learn from most of my colleagues. You're not going to use the specific facts. So you can go to a book and you can read facts as you need them. You need to know what to read. You need to have enough ideas to know what you should look up and put into the search bar. But even there, you only have to be somewhat close. What you really need is ways to look at problems and see relationships. So do we agree that the area is a function of the hypotenuse and the angle? Because if I give you the hypotenuse, we know that B is actually equal to C cosine X, and A would be C sine X. So the area would be 1/2 C squared sine X cosine X. So we know that the area is a function of the hypotenuse and the angle. Moreover, we know it has to be proportional to the square of the hypotenuse. If I triple the hypotenuse, I triple the two sides, and if I triple the two sides, then the area goes up by a factor of 9. So does everyone agree that the area has to be proportional to C squared? And the proportionality constant can change as I change the angle. It's going to be 1/2, sine X, cosine X, whatever hell function that is. But we have this relationship. Okay, now, I told you earlier, almost every good geometry proof requires you to draw an auxiliary line. We are trying to prove the Pythagorean formula about right triangles. Can anybody give me a good auxiliary line to draw? What line should I draw?
You could cut the existing right triangle into 2 right triangles by drawing a line through the existing right angle.
Good.
That are orthogonal to the hypotenuse.
Perfect. That is exactly the line we should draw. And because we have no originality, we call the new triangles triangle 1 and triangle 2. Okay? Which maybe is an insult to the Greeks to be using Roman numerals for them, but oh well. All right. So what is really nice is if you do a little bit of geometry, you will see that the angle down below is the same as the angle in the other corner, that these 3 triangles are all similar. Now, what's nice about this is we know that the area is proportional to the square of the hypotenuse. We now have 3 smaller combined to get you the large one. So when we put it together, we get f of x times a squared plus f of x times b squared is f of x times c squared. And why can I divide by f of x? So can I just divide by x, by f of x? This is a math. It can't be 0, right? You've got to be careful about making an assumption. Never assume. You have to say, if I'm dividing by f of x is not 0. What would it mean if f of x is 0? It would mean the triangle has 0 area. Okay, I know f of x is not 0, so I can do this. And this now gives us the Pythagorean formula. There's a lot more you could do with this. I I'm not going to go too far into this. I will just give you one more example from physics. Let's say we're looking at a pendulum. So we have a mass m, acceleration due to gravity g in meters per second squared. Mass is in kilograms. The length of the pendulum is in meters L. The initial angle x is in radians, which is unitless. If I want to figure out how long it takes the pendulum to swing, that's in seconds. And so then the question becomes, how can I combine these units to get seconds? The only way is I have to take length divided by the square root of divided by the gravitational acceleration g. That's going to give me 1/seconds squared. I'm sorry, that's going to give me seconds squared. So when I take the square root, that's going to give me seconds. That's the only way I can get seconds from these quantities. The mass doesn't come into play. There's nothing to cancel the mass. Now, it could come into play, the angle could come into play in terms of the constant outside. But I know before I do any experiments, if I quadruple the length, the period should double. And it's wonderful to be able to look at problems and get a feel like this before doing long, tedious calculations. Okay, so now let's go now towards stuff we're going to be doing for probability. So this is the gamma function. This is the generalization of the factorial function. The first thing you should always do when I give you an integral is make sure it exists. And so I claim that as long as the real part of s is greater than 0, this exists. And we talked last time about why the hell would you define it as x to the s minus? We define it like that because we can really view it as x to the s times dx over x. And so now if I do a multiplicative change of variables, if I replace x by 5 times x, then dx over x is unchanged. So it just turns out this is the good, convenient way of defining things. Big of a deal to just add 1 or subtract 1. When we were doing the negative binomial, we mentioned that there were at least 3 different ways to define what the hell you're studying. They all differ by a simple shift, so it's not a big deal. So if you want to make sure this exists, where are you worried about this integral existing? What could give you problems? Yeah.
It blows up at 0.
It could blow up at 0, and what else? Yeah, does it go to 0 at infinity? And if so, does it go to 0 at infinity fast enough? So at infinity, we're okay. And the reason is e to the minus x decays much faster than x to the s minus 1 grows. How could you prove that rigorously? So one thing we could do is we could look at, x to the s minus 1 over e to the x. This is going to be less than or equal to x to the s minus 1 over x to the m over m factorial. Because I'm taking just one term in the exponential. So if I take just one term in the exponential, I make the denominator smaller, which makes the fraction larger. So this is going to be less than or equal to 1 over x squared if m is greater than, say, the absolute value of s plus 100. I don't need the plus 100. Why am I putting in the plus 100? Because I don't want to risk doing a mistake, calculating something, live. Doesn't really matter. I just need to know that it's decaying fast enough at infinity. If it's decaying like 1 over x squared, I'm okay. So as long as I choose a term that's sufficiently large, I'm fine. I'm not going to try playing the game as to what's the smallest term I need to. There's no point. It's not going to get me anything better. All right, so we know we're okay near infinity. Now the next thing is near the origin. So near 0, e to the minus x looks like what? So if x is really close to 0, what does e to the minus x look like? Not infinity. You have e to the 0 is 1. It looks like e to the 0, which equals 1. So as we get really close to 0, e to the minus x is going to just look like 1. It's all going to come down, what does x to the s minus 1 look like? So we need, the integral of x to the s minus 1, let's say from 0 to epsilon dx to be finite. Right? And so if we want that integral to be finite, what do we need to be true? Well, if s is real, so we know that this integral x to the s minus 1 dx in absolute value is less than equal to the integral from 0 to 1 of x to the real part of s minus 1 dx. And so if you're not comfortable with this, just pretend s is real for the whole time. It's fine. So if s is real, we want to integrate from 0 to epsilon x to the s minus 1 dx. What does that integral equal? What do you get when you integrate x to the s minus 1? X to the s over s. Does everyone agree? Everyone agrees? Always? No matter what real s I give you, you're going to get x to the s over s? There's no s you have to be careful about? I could be doing this just to psych you out. Yes. Not 1. You're close. What's the one value of s you have to be careful about where the 0? If s is 0, what do you get? You get ln of x. So this is if s does not equal 0, if s equals 0. So if s is positive, then this is okay. If s is negative or 0, we're not okay. So we're okay if the real part of s is greater than 0. We're not okay if the real part of s is less than or equal to 0. So again, this is just standard integration. When does x to the s minus 1, when is that integrable? I need the exponent to be greater than negative 1. And as long as it's greater than negative 1, we're fine, and this integral will make sense. Okay, so at this point, we now have a function. We've named it. It makes sense for certain values of s, and we have no idea why we care about it. So the way you find out is you try looking at special values. If you were told, and given that I'm the professor, it's quite likely you're about to be told that you have to evaluate this for value of s, what value of s would you choose? 1. Yep, so I saw somebody drinking raisin wine. 1 would be the most natural thing to try. Why would you try 1? Yeah, s minus 1. Not only is s minus 1 a constant, it's always going to be a constant because s is fixed. What constant is it going to be? 0. It's going to be the simplest thing to do. So I would evaluate this when s equals 1. And then once you have that successfully done, what would you do next? After doing s equals 1, try s equals 2. And after that, 3. And so these are just going to be integrals e to the minus x times x squared, x cubed, x to the 4th. These are just moments of the exponential function. You should be able to do these. Okay? It turns out that you can show gamma of s plus 1 is s gamma of s. So this is a recurrence relation. So what this allows you to do is once you know it for one integer, you know it for the integer one more than it. Now again, you could just do it by brute force and just start doing things directly. But if we prove this relationship, then we get everything very easily.
That's true because it's the factorial.
And in fact, that's why you can see the factorial. So now, if gamma of 1 equals 1, gamma of 1 plus 1 is gamma of 2, is 1 times gamma of 1 is 1. And then gamma of 2 plus 1 is gamma of 3, is going to be 2 times gamma of 2, which is 2. Gamma of 3 plus 1 is gamma of 4, is 3. Gamma of 3 is 3 times 2. And at this point, we realize we shouldn't be writing 2. we should be writing that as 2 factorial. So we should write this as 2 factorial. We should write this as 3 factorial. We should write this as 1 factorial. And, you know, gamma of 1 is 1 times I'll just do it like this. So if we know gamma of 1 is 1, we then get gamma of 2 is 1, gamma of 3 is 2 factorial, gamma of 4 is 3 factorial. It seems like gamma of n plus 1 is just n factorial. It's just shifted over by 1. So let's prove this. So we want to integrate gamma of s plus 1 is the integral from 0 to infinity of e to the negative x, x to the s plus 1 minus 1 dx. So it's the integral from 0 to infinity of e to the negative x, x to the s dx. What proof? How do you want to do this integration? It seems to be screaming integrate by parts. We could, of course, attack this by differentiating identities and using the exponential function, but this seems to be screaming at us, let's use integration by parts. Most of the time, there's only 2 choices when you do things with integration by parts as to what should u equal and what should dv equal. If you get it wrong, what should you do? Try the other, right? It's really nice in life when you only have 2 options. So we have to choose u and we have to choose dv. Do you want the exponent of s to be going up or down? Down. So let's make u be x to the s. And then dv would be e to the minus x dx. du would be s x to the s minus 1. V would be negative e to the minus x. And we're going to use the integral of uv from 0 to infinity is equal to, u dv is equal to u at infinity. I'll do it this way. uv at 0 infinity minus the integral from 0 to infinity of v du. I know it has probably been a while since some of you have done actual integration. And so I find that if I have to do integration, it is best for me to just put everything explicitly down on the board. You know, here's the formula I'm going to be using. I'm using my integration by parts. Here's what u is dv, du, v. I now just have to substitute in directly. And so I get gamma of s plus 1 is uv. So I'm going to get x to the s negative e to the negative x. So negative e to the negative x at 0 infinity. The minus and a minus becomes a plus, integral from 0 to infinity of v du. So it's going to be s e to the negative x, x to the s minus 1 dx. All right, well, when I look at x to the s e to the minus x, when x goes to infinity, what do I get? So as x goes to infinity, what does the boundary term go to? Which is going to win, e to the minus x or x to the s? It's going to go to 0. So that's what we showed earlier, that it's going to decay fast enough at infinity that I don't have to worry about the upper boundary term. What about the other term? What about when s goes to 0? Well, e to the minus x looks like 1. And because we're assuming the real part of s is greater than 0, that's going to be x to a positive power, so that's going to be 0. And so here I'll add, real part of s greater than 0. I can pull out the s from the integral, and I'll have the integral from 0 to infinity of e to the negative x, x to the s minus 1 dx. Hopefully it's now clear why I chose to write it in that order. What's that integral equal?
Yeah.
Just gamma where? Gamma at what point? At s. And that's the relationship we were trying to prove. So we just proved gamma of s plus 1 is s gamma of s. And then note that, gamma of 1 is the integral from 0 to infinity of e to the minus x, x to the 0 dx. That's just the integral from 0 to infinity, e to the minus x dx. which we've done several times, is 1. This is just an exponential with parameter 1. What's nice is you don't have to care about which exponential definition are they doing. Are they doing e to the x over lambda or e to the omega x? They're both the same when lambda equals 1. This integral is just 1. We now know that the gamma function is going to be gamma of n plus 1 is going to be n factorial if n is a non-negative integer. And because it's representable as an integral, there is a hope that we can use some advanced mathematics to attack this. So if you take a course in real analysis, if you take a course in complex analysis, we can study this. The factorial function occurs all the time in combinatorics. Being able to understand it is extremely valuable. And so, we basically just shown here that gamma of n plus 1 is n factorial. This is just worth really extracting. If you wanted to do this by brute force, you could calculate this. If you want to, you could calculate gamma of 4 is the integral from 0 to infinity, e to the negative x, x to the 4 minus 1 dx. That'd be integral 0 to infinity, e to the minus x, x cubed dx. If you had to do this, what would you do? If I just gave that to you as an integral 2 days ago, how would you attack it? You plug into calculator. There's been an electromagnetic pulse. Wouldn't you? Yes.
Tabular integration.
Yeah, tabular integration by parts. You would just have to do integration by parts multiple times. And then if I then gave you after that, if I then gave you gamma of 11, you would have to do it all over again. And so the whole point of what we just did is this is similar to extracting rules of differentiation. We don't want to calculate the derivative of x to the n for every n. We want to find the general rule that the derivative of x to the n is n x to the n minus 1, and then we can just keep using it. It's the same thing here. Once we've established this recurrence relation, we get immediately that gamma of n plus 1 is n factorial. We don't have to keep doing all these integrals. That's extremely useful. Now, you can prove a bunch of identities. And so the book gives a proof of what's called the cosecant identity. Gamma of s is gamma of 1 minus s is pi over sine of pi s. Why do you think I would take s equals 1/2? Why is that a good choice of s to use?
Is that on the left-hand side?
Yeah, because if we take s equals 1/2, then you get gamma of a half, gamma of a half. You can now solve for gamma of a half. And you get the square of gamma of a half is pi over sine of pi halves. What's the sine of pi halves? Or the sine of 90 degrees. It's just 1. So this gives you gamma of a half is the square root of pi. If we take the fact that we've just shown gamma of n plus 1 is n factorial, this is kind of saying negative 1/2 factorial is the square root of pi. This should clearly not cause any confusion. Nobody should be thinking that the number of ways to arrange negative 1/2 of a person is the square root of pi. But the function that is the same as the factorial function, where they're both defined, makes sense in other places. It turns out you have seen this before. You have seen gamma of 1/2 equals the square root of pi. Does anybody know which function you've seen this in? Where have you seen a square root of pi in probability of statistics? Yes. The Gaussian. It's actually related to the Gaussian. It's related to the normalization. Another beautiful identity is what's called the beta function, which we define as the integral of t to the a minus 1, 1 minus t to the b minus 1. And your first thought should be, are you doing this to me again? Can't you just define things to the a and the b? Why do you have to do a minus 1 and b minus 1? It's because I know the punchline. Because I know the punchline, we define things like this so that the resulting formula becomes nice. It's not a big deal to define it another way, but this integral, it turns out it's just gamma of a over times gamma of b over gamma of a plus b. It's a nice exercise to try to prove that directly. The simplest is to move the gamma of a plus b over to the other side, write that as an integral, try to expand things, and then you have two integrals on the left equals two integrals on the right, and play some games. I believe it's in the book. As a nice exercise, try to do that. Once we have this, notice that what we have inside the integrand is non-negative. And so if we just divide by what it equals, we have a probability distribution. So what do you think we should call it? In a shaka, we'll call it the beta distribution, coming from the beta function. And so if we just divide by what it integrates to, we now have a nice density. And what you can do is you can say, let's look at different values of a and b and see what shape we get. And this is going to be a distribution supported on 0 to 1. So this could be a really good way to model maybe the probability of an event, because this is only going to give you numbers between 0 and 1. So maybe my probability of something happening comes from a beta distribution. And not surprisingly, the very next plot is similar to what we saw for the baseball talk. Here are some plots of different beta distributions. And you can get a sense for what kind of shapes can you get. One of my favorite shapes is this one. Oops. No, I'll do it this way. What does that maybe kind of look like? Yeah, it kind of looks a little bit like a normal. Do you think it could be a normal? No. Why can't it be a normal? What's the largest value it can take? 1. What's the smallest value it can take? 0. It can't be the normal distribution. But it could be really close to the normal distribution. Maybe if a and b get really large, this could converge to a normal distribution. It won't be exactly a normal distribution, but it could be close enough. And we saw early in the semester when we were adding a bunch of uniform random variables, it very quickly looked like a normal distribution. We could write down a god-awful explicit closed form expression that nobody would want to work with. And the goal is, can I somehow approximate a complicated function with something simpler? And so I'm not going to do the calculations here. This is what I said is I'm going to let you do the integration at home. I'm putting it here on the slides. If I take the normal, let's look at the standard normal. So the mean is 0, the standard deviation is 1, and I want to calculate the 2mth moment. Why am I not calculating the odd moments of the standard normal? Why am I only calculating the even moments of the standard normal? What are the odd moments? So if I integrate x times e to the negative x squared over 2, what would I get? 0. All the odd moments vanish. So there's no need to calculate the odd moments. So I know the odd moments are 0. Let's calculate the even moments. We can do this by differentiating identities. We can do this by integration by parts. There's lots of things you can do. We have to start off by knowing that the integral, when I take m equals 0, is equal to 1. This is just the normalization constant, which we've done before. And then as a little bit of an exercise, if you go through, you can see that by playing games, we can adjust things so it's the gamma function. And we just do a change of variables, let u equal x squared over 2. So x is equal to the square root of 2u. And then dx becomes the 1 over the square root of 2u times du. When the dust settles, you can see, when I take m equals 0, I just get 1 over root pi times gamma of 1/2. If this integrates to 1, then gamma of 1/2 has to be the square root of pi. And more generally, you can then get that the 2mth moment is just 2 to the m over square root of pi times gamma of m plus 1/2. So the moments, the even moments of the standard normal are related to the gamma function at half integer arguments. So again, strongly urge you to go through and do the calculations. Okay, so now this is just, so everything is in the same place. We talked about the Weibel distribution last time. We talked about how useful it is. Instead of using the Weibel, you can also use the gamma distribution. The gamma distribution looks very similar. The big difference is over here, instead of having that to the kth power, I have that to, hello? Okay, all right, yep. We just had somebody in the waiting room, which is exactly why I always check that. Okay. Okay, and so the difference is between the gamma and the Weibel is in the Weibel, this is to the kth power, and that's k minus 1. Over here, this is to the first power, and that's to the k minus 1. Is there a value of k where these are the same? Is there a value of k where these are the same?
K equals 1.
Yeah, k equals 1. So k equals 1, both the gamma and the Weibel are the same, but in general, they're going to be slightly different. And which one would you rather do integration with, the gamma or the Weibel?
Probably the gamma.
Why the gamma?
Well, I'm very simplistically thinking that it's a special case of the Weibel, so it can't be hard.
It's not a special case of the Weibel because they have different powers. So, again, remember over here, this is to the kth power, this is to the first power. I think the Weibel is a little bit easier because if you let u equal x over sigma to the k, then du is going to be 1 over sigma x over sigma to the k minus 1 dx. And that's exactly what you want over here. It just changes variables nicely. So I think the Weibel distribution is going to be a little bit easier to integrate than the gamma. They're both nice distributions, and there's lots of results known in both of the cases. And you always just want to make sure that you do have a probability distribution, that things do integrate to 1. So as a nice exercise, go through and using the definition of the gamma function, show that these integrate to 1. You've got to be a little bit careful because in the gamma function, we have e to the negative x. Here we have e to the negative x over sigma. All right, I have to rescale. Not a big deal, but you have to do it. In the other one, you have x over sigma to the k. I have to do a change of variables. I have to let u equal x over sigma to the k. Strongly urge you to do these calculations and make sure that your integration is good enough to do these and show that they integrate to 1. So again, if you have trouble, talk to me, talk to the TAs, but make sure that you can show that these really are nice probability distributions. Okay. The next one to look at is the chi-squared distribution. So how many of you have seen chi-squared in a statistics class? A good number of you. Okay. And have they defined it like this? No? Wait, you've seen the chi-squared, but they haven't defined it like this?
Concept, but they just always use a calculator, like stat 202 or something.
Okay, I think we have fixed the technical malfunction. Excellent, yes. These things occasionally do happen. Okay, so we can now define properly a distribution, which we will call the chi-squared distribution with new degrees of freedom. And if you look at it on the right, we have f of x is equal to some nice expression, and there's a free parameter nu. And depending on the value of nu I choose, I'm going to get a different result on the right. The first thing, of course, is to make sure that this integrates to 1. And so I will remind you on the right, what is the gamma function? Gamma of s is the integral of e to the negative x, x to the s minus 1 dx. So we just want to show that this integrates to 1. So if you look at it, we have e to the negative x halves in the definition of the chi-squared distribution. And in the definition of the gamma function, we have e to the negative x. Yet again, we have different normalizations. It's wonderful, right? You have to constantly be converting from one integral to another. It's not a big deal. Let x over 2 equal u, so dx is equal to 2u. And when you do that, you can go through and you can then show that this does equal a gamma function at basically gamma of nu halves. And the extra 2 to the nu halves is going to come from the fact that x over 2 is equal to u. So again, strongly urge you, go through the exercise and show that this does integrate to 1. But you can see it's almost the gamma function that we're integrating. It really looks like it's gamma with s equals nu halves. The only reason it's not is because we have an e to the negative x over 2, not e to the negative x. So we just have to do a change of variable. Okay, and that's not going to affect the fact that we get a gamma of nu halves. It's just going to affect the powers of 2. So this is yet another distribution we can look at. You should always, of course, ask, who cares? Why do we want to look at this? So did anybody take a stats class where they told you why you care about this distribution? All right. I think things have been fixed again today. Excellent. Yes, we seem to be back on recording. Okay. So why do we care about the chi-square distribution? Well, if you look at it, here's a bunch of different plots for different values of nu, 1, 2, 3, 5, 10, 20. You can see as nu gets larger, its mass is shifting to the right. Does the shape look interesting to you? Does it look like it's converging to anything? Any thoughts about what it might converge to? Yeah, when in doubt in this class, if I'm asking, what do you think something converges to as it gets larger and larger and larger? Normal is a pretty good guess, right? So it looks like it's converging potentially to a normal distribution. Now, it turns out that if x is a normal random variable, standard normal, then x squared has a chi-square distribution with 1 degree of freedom. Why is this important? Well, a lot of times when you're doing statistics, you might look at observed minus predicted. Well, if I look at observed minus predicted, positive errors can cancel with negative errors. So to avoid positive and negative errors canceling, there are 2 things you can do. One is you can put in absolute values. Unfortunately, the absolute value function is not differentiable, and that means all the calculus you've taught is not useful. But it's a good thing to do. But there's a huge cost. All those math classes can't be used. So instead of using absolute values, how could you handle things? Square. And so that's why we often look at sums of squares of errors, because now calculus is applicable. And we will see a great example of this later in the semester. And so it's useful to know maybe the errors are normally distributed. Maybe the predicted values and the observed values, maybe the observed values are normally distributed about the predicted values. And so if I look at the sums of squares of errors, I need to know what is the square of a normal random variable. So there's lots of ways we can do this. One is the CDF technique. So let's let y equal x squared. X is normal with mean 0 and variance 1. So if I want to calculate what is the probability that y is at most y, is it possible for y to be negative? No, y is x squared. So y is never going to be negative. So you're a chi-squared random variable, which doesn't take on negative values. If you go back to the definition of a chi-squared random variable, for x greater than or equal to 0, it's the following. For x less than 0, it's defined to be 0. So it's not a proof that it's going to be a chi-squared random variable, but it's at least in the running. All right, so if I want the probability that big Y is at most little y, this is the same as the probability x squared is less than or equal to y. And how would you calculate the probability that x squared is at most y? What's that the same as? So if I want big X squared to be at most little y, what would that be about X? Nope. You're close. Plus or minus. Because if it was negative 14 billion times the square root of y, it would be less than the square root of y. You could say the absolute value of x is less than the square root of y, or negative root y less than or equal to x less than or equal to square root of y. So this is the same as, do you agree that it's just the same as twice the probability 0 less than or equal to x less than or equal to the square root of y? Because x is a symmetric random variable. It just makes my life a little bit easier. So this is just twice the integral from 0 to the square root of y, and then the density of the standard normal. So we need to integrate the standard normal, right? Unfortunately, there's no closed form expression for it. That doesn't bother us. We can just write down big F of x at root y minus big F of x at 0. This is the beauty of the CDF method. What are we going to do on the very next line? Differentiate. So this is equal to the cumulative distribution function of the square root of y. So I apologize, you are now at the advanced part of the lecture. So one of the things we showed is that, have you seen probability densities before? Okay, so probability density, it's a function that's non-negative and it integrates to 1. So f sub x is a non-negative function, it integrates to 1. Capital F is the cumulative distribution function. It's the probability you take on a value that large or smaller. What's the probability I'm at most the square root of y? And so it turns out, have you done calculus? Yeah. Okay, so it turns out if you do calculus, the derivative of the cumulative distribution function is the density, or the integral of the density is the cumulative distribution function. So if I want to calculate the probability that y is at most little y, that's its cumulative distribution function. The derivative of that will then be the density of my function, which I'm trying to find. So when I take the derivative, I get the density function of y. Oops, this is not square root of y, this is just y. Is equal to the derivative of the right-hand side. So I'm going to get 2, the derivative of my density function at square root of y times the derivative of square root of y minus 0 because I'm taking the derivative of a constant. Okay. What's the derivative of the antiderivative of little f of x? Yeah. So this is just going to be twice little f of x at square root of y. And then the derivative of square root of y is going to be 1/2 y to the minus 1/2. So this is going to be the 2 and the 1/2 cancel. So I'm going to get y to the minus 1/2, 1 over square root of 2 pi, e to the negative. Now the Gaussian, the standard normal, is negative input squared over 2. So what's the square root of y squared? Y over 2. Now the last thing to do is this is the same as 1 over the square root of 2 pi, except I'm going to write this really carefully. Square root of 2, let's do it this way. 1 over 2 to the 1/2, gamma of 1/2, because we know the square root of pi is gamma of 1/2. Y to the minus 1/2, I can write that as y to the 1/2 minus 1, e to the negative y halves. And now I've written that as you would write a chi-squared random variable with 1 degree of freedom. So this is a chi-squared random variable with 1 degree of freedom. So if you go back to, oh, that's right. I knew what was coming. And so I made sure to keep the density in the upper right corner. I want 2 to the new halves, gamma new halves, x to the new halves minus 1. And that's why I wrote y to the minus 1/2 as 1/2 minus 1. That's why I wrote the square root of pi as gamma of a half. So that it's now perfectly set up so that I can see it is a chi-squared random variable. So the square of a standard normal is a chi-squared random variable. That's useful. What would you think? Let's see, we summed normal random variables before, and we saw normal plus normal is normal. We could sum chi-squared random variables and ask, what happens if you sum chi-squared random variables? So one of the things to do is to try to calculate what is the mean, what is the variance of a chi-squared random variable with 1 degree of freedom. So there's a couple of ways you could try to do this. If I want to calculate this mean, what's your first thought? So if I pull out the constants, I get 1 over 2 to the 1/2 gamma of 1/2 integral 0 to infinity x to the 3/2 minus 1 e to the minus x halves dx. What does that integral almost look like? It almost looks like a gamma function. So would be gamma of 3/2 if had e to the negative x, not e to the negative x over 2. So let u equal x halves and change variables. So the whole point is, it's actually really easy to calculate the mean, the second moment, any of the moments of a chi-squared random variable. It's not going to be a challenge at all. It's just going to be another gamma value. Okay, so I'll leave that as an exercise for you to do. Here is the big result. And one of the reasons why chi-squared random variables are so important. Imagine we have a bunch of standard normal random variables. Let's assume they're all independent. And so each xi is normal, mean 0, variance 1. And we'll let yk be the sum of the squares of the x's. Okay? Then it turns out that the y's, that yk is just going to be a chi-squared random variable with k degrees of freedom. So if I take the squares of k independent standard normals, it's a chi-squared with k degrees of freedom. One way of looking at that is I'm summing, because I know each x squared is a chi-squared with 1 degree of freedom. I'm summing k chi-squared random variables with 1 degree of freedom. I get a chi-squared with k degrees of freedom. Maybe this is true in general, and it is. So if I assume that each y nu I is a chi-squared with nu I degrees of freedom, when I sum them all up, it's a chi-squared with the sum of the nu's as the degree of freedom. So this is very similar to Gaussian plus Gaussian is Gaussian, just with a different mean and variance. Chi-squared plus chi-squared is chi-squared, just with a different number of degrees of freedom. And so if we can show that this is true for the sum of 2 chi-squareds, we get it immediately for 3 or 4 or 5 or any finite number. And the reason is, if I have y1 plus y2, that's going to be a chi-squared with nu1 plus nu2 degrees of freedom. Then I have the sum of 2 chi-squareds, one with nu1 plus nu2 degrees of freedom, one with nu3. It's a chi-squared with nu1 plus nu2 plus nu3 degrees of freedom, and so on and so on and so on. So all I have to do is, if I can show that if I have 2 chi-squareds with nu1 and nu2 degrees of freedom, and I add, I get a chi-squared with nu1 plus nu2 degrees of freedom. That's not bad. Everything follows from that one calculation. I'm not going to go through things carefully right now. Given some things I might have heard during the equipment malfunction, I'm not really confident about asking about multivariable calculus right now. So there are ways to write things down involving Jacobians, change of variable formulas, and whatnot. I'm going to put that on hold for now. And so let's say we want to calculate the density of 2 chi-squared random variables with nu1, nu2 degrees of freedom. Oops. And so, okay. And so we've shown earlier in the semester that the density of a sum is the convolution. So if you haven't seen this before, if I want the sum of my 2 variables to equal y, if the first one takes value t, the second has to take value y minus t. And so if I integrate over all possibilities, if the first one ranges over t, the second one ranges over y minus t. So their product is going to give me the probability of summing to y, where the first one is t and the second one is y minus t. So I have to do this integral. So the c nu1, the c nu2, these are the normalization constants. Does this look like a pleasant integral to do? If it does, you need help, okay? This should look like a monster. I can pull out the normalization constants. I'm going to have the integral from 0 to y of t to the nu1 over 2 minus 1, y minus t to the nu2 over 2 minus 1. I have an e to the negative t halves. I have an e to the minus y minus t over 2. Oh, wait a minute. The e to the negative t halves cancels the e to the t halves in the other one. Right? So things are not quite as bad. I can pull the e to the minus y over 2 outside the integration, and I'm left with this integral to do. Does that integral look like anything you've seen before? We did see something close to this earlier today. If y equals 1, this is something you saw earlier today. Let's see. This one. If y equals 1, it's the beta distribution. So we've talked a little bit about the theory of normalization constants. That if I can identify the x dependence of an integral and see that it matches a known probability distribution, I'm done, because the normalization constant is then forced upon me. I just have to see, what does this look like? This looks a lot like a beta distribution, except I have a y rather than a 1. So I need to change variables. I need to replace t with something. And the great insight is, I have y minus t. How could I pull the y outside the integral? I should write t as what? So this is the key insight. I want to be able to pull a y outside. I should write t as what? It's telling me y is the natural scale I should be looking at things. I'm integrating from 0 to y. So I should write t as a multiple of y. Let's try writing t as y times u, where u is my new variable. Then dt would be y du. T goes from 0 to y, becomes u goes from 0 to 1. So now I get c nu 1, c nu 2, e to the negative y halves. I've got the integral from 0 to 1. The t is just going to be yu. So this is going to be y to the new 1 over 2 minus 1, u to the new 1 over 2 minus 1. Then I've got the y minus t. Since t is equal to yu, I can pull out a y. And so I'll have a y to the new 2 over 2 minus 1, 1 minus u to the new 2 over 2 minus 1 du. And the du has an extra factor of y with it. Okay, so this is c nu 1, c nu 2, e to the negative y halves. I'm just pulling out now everything from the integral that doesn't depend on u. So I've got y to the new 1 plus new 2 over 2. I've got a minus 1, and then a plus 1 from the y, so it's a minus 1. And then I have the integral from 0 to 1 of u to the new 1 over 2 minus 1, 1 minus u to the new 2 over 2 minus 1 du. This is just something independent of y. There's no y dependence. It's a number. So let's call it c. Well, we've already got. Let's call it maybe gamma nu 1 nu 2. So now we get c nu 1, c nu 2, gamma nu 1 nu 2, e to the minus y halves, y to the new 1 plus new 2 over 2 minus 1. And if you look at this, that is a chi-squared random variable with new 1 plus new 2 degrees of freedom. So this is the functional form of a chi-squared random variable with new 1 plus new 2 degrees of freedom. This constant over here then just has to be whatever constant I need. And in fact, you can use this to actually prove the normalization of the beta function and the beta density. Because we know this has to be the normalization constant of the chi-squared distribution. So this has to be C nu 1 nu 2. So this whole thing here has to equal C nu 1 plus nu 2. And that will give you the normalization of the beta. So I really hope you can appreciate from this how powerful the theory of normalization constants is. We don't have to do this painful integral. That should look like a very painful integral to do. We are completely bypassing that. By figuring out how things depend, by doing this wonderful change of variables, all I have to do is get a sense of the y dependence. The rest is fixed on me. I don't have to integrate that. Now, if I remember my beta distributions, sure, I can see what that is and everything, but I don't need to. Everything works out nicely. We now know the sum of two independent chi-squareds is just a chi-squared where you sum the degrees of freedom. All right. I'm going to skip the sums of squares by the change of variable formula. I'm not going to risk going into that. I want to just end briefly with Markov's inequality. So Markov's inequality says, imagine we have a non-negative random variable, so it can't take on negative values. And we want to find what is the probability you could take on a certain value. Can we get some upper bounds? The more we know about the distribution, the more we can prove. Let's assume we only know the mean. Okay? This is not always going to be the case. So for example, I might have a distribution where I don't have a mean. I could have the Cauchy distribution. The Cauchy distribution, however, is not non-negative, but I can give you some things related to the Cauchy distribution that don't have a mean. But let's imagine we have a distribution that has a mean. Is it possible to have a high value? And the answer is yes, so long as it doesn't happen too often. And the higher the value above the mean, the less likely it is. And so what this is telling us is the probability that x is at most a is at least 1 minus the expected value of x over a, or equivalently, the probability that x is greater than a is at most the expected value over a. Can somebody give me a value of a where this is useless? So here's an inequality. The probability that you're at least a is at most the expected value of x over a. When would this be useless? It does. It just tells you the probabilities at most infinity. If a is 1, it might be useful. You have to answer relative. What's the only number in play here? I've given you the expected value of x. Your answer has to somehow be related to the expected value of x. For what value of a is this useless? So if it's the expected value of x, then the probability that you're at least a is at most 1. If a is less than the expected value of x, the probability that you're at most, say, a half the expected value is at most 200%. Useless. This only starts to become useful once a is greater than the expected value of x. So if a is greater than the expected value of x, you start getting some information. And so at the very bottom, I imagine the situation, the most extreme case possible. Imagine you want to have a value that is large. And I'm going to write it as the expected value of x over 1 minus p. So as p gets closer and closer to 1, then this is going to get larger and larger and larger. Is it possible? Could I have a value that much greater than the expected value? Yes, if its probability of happening is very, very small. So if the probability that it happens is 1 minus p and all the other mass is at 0, that's going to make the expected value as small as possible. If I want to balance out this large value, the best way to balance it out, the best way to deal with it is to put as much mass as I can at 0. And so I put all of the mass I can at 0 and the minimum I need at that large value, then I've rigged things right now so that the expected value is x. So this tells us that I could get something with extremely large value relative to the expected value. But the probability of that happening is tremendously small. And the further away I am from the mean, the less likely it is. And the natural scale to measure things is the expected value of x divided by a. Okay, so the proof is not too bad. And so for the proof, let's calculate what is the probability that x is greater than or equal to a. This would be the integral x, I'm sorry, equals from a to infinity of the density, right? Now, I want to somehow compare this to the expected value of x over a. Right? So I want to try to find what is a good way to compare these things. Do we know the expected value of x? We know the expected value of x is the integral from 0 to infinity of x times the density. This is a natural thing to look at because I'm claiming that my probability is at most the expected value of x over a. So I should somehow use this. Well, I want the expected value of x over a. So what should I do to both sides? Divide by a. Okay. Now, if I look at x over a, if x is greater than a, what can you tell me? What is true about x over a? I'm sorry? Right. So is it going to make things larger or smaller? So if I just integrate from x equals a to infinity, x over a times the density, have I made things larger or smaller? If I don't include the integral from 0 to a. What have I done to the probability? I've thrown some probability away, possibly. So I can't have made things larger. And in this region, so in this region, we know x over a is greater than or equal to 1. So if I replace that with 1, what do I do to the integral? I can't make the integral larger. So the integral can't be getting larger. And over here, this is just the probability that x is greater than or equal to a. And that's the proof. So this is a proof of Markov's inequality. We start off with what is the expected value of x? We show that if we want to calculate the expected value of x over a, if we drop the integral from 0 to a, we can't have made the probability larger. If we replace x over a with 1, we can't have made it larger, and now we have a bound. So we'll do Chebyshev on Thursday. This is a good place to stop. All right, have a great day all.